like to talk to you about a reduced water footprint in vertical cities. So if you look at carbon and water footprint, what will become more important in the future? And we had the presentation on transport and CO2. Well, actually, water footprint will become more important in the near future than CO2 emissions. If you look at the amount of water that we would actually need, or we actually need to produce the products that we daily consume, for instance, a staggering amount of water that is needed for a kilogram of chocolate. You see the amount of square kilometers of water that is used in the industry, in the agriculture and your daily homes. And looking at 7 billion people at the moment, and it's growing by 2.4 billion in the coming future. So, having said that, there is actually a high theoretic availability of water in the world. If you look at the average precipitation, it is 814 millimeters of water per year. Well, actually, this amount of water, 61% will evaporate. So theoretically, there will be 39% available for potable and non-potable water use. So per person per day, that would actually mean 5.8 thousand square meter or cubic meter of water per year, which is 16,000 liters. That's very much. But as we see, all this water is not available, actually, this 39%. We see water as being very unevenly distributed throughout the world. I mentioned 814 millimeters per year. If you look at countries in the northern part of Africa, there's actually only 51 millimeters of water available per year. And if you look at countries like Latin America, Brazil, there's actually an amount of water available far beyond 2,000 millimeters per year. So that's very unevenly distributed over the world. And besides that, the accessibility, the water is not accessible. Part of this 39% is just not available. We cannot get it. And also over time, this water is not available. So there might be peaks in monsoon. So if we look at low precipitation areas, for instance, like I said, the north part of Africa, Egypt and Libya, there are the two lowest precipitations in the world. Egypt at 51 millimeters per year, that's nearly nothing. But they have the River Nile, so they actually have a high availability of water. And if you take a neighboring country like Libya, they have about the same precipitation availability per year, which is next to nothing, but they don't have the River Nile. So there's actually a very low availability of water in Libya. So a very high water stress. Water excess over time. Look at a country like India. It rains a lot, but it's actually being concentrated by between 80 and 85% in the monsoon area. And I was in India 2 months earlier, in Mumbai, and maybe you've heard that in Mumbai the mousson this year was actually very much worse than other years. And we're actually traveling to Mumbai, and all the trains and the planes were cancelled, and we had a conference, and nobody was able to come. There was such a high water stress on the surplus side. If you look at a country like Australia, where we are now, this is one of the driest continents that is in the world, covering 6% of the landmass, but only 2% of the available precipitation in the world. But actually, Australia has a high availability of water, but as the previous presenters mentioned, the population is very much concentrated on the coastal lines. So there's a high water stress because it's highly concentrated. And a good illustration of the water stress and how this can turn into a disaster is the Sao Paulo 2014 water crisis. So in October 2014, one of the worst droughts hit Sao Paulo and neighboring states. And the key reservoirs only held 2 weeks of drinking water. And this might seem a lot, but their normal reservoirs would be maybe 5 or 10-fold of this. So there was quite a high water stress. So Sao Paulo is one of the largest and richest cities. How can this city run out of water? Well, if you look at the concentrated water stress that they actually have in Brazil, if you look at the Amazon, there's actually a very high availability of water, of course, in the Amazon. It rains a lot. But 90% of the people actually live on the coastal line. So 40% of these people on the coastal line actually face a medium to extremely high water stress. So a country over 200 million people, of which 90% is urbanized, makes this a problem of 36% of the population there. It's actually a staggering amount of people. So another problem they are facing is actually the variability of water supply. That means an inter-annual discrepancy. So one year it might rain more than other years. And also the seasonal variability is very high. So in spring, summer, fall, and winter, there's different precipitation levels. And what of course is happening there, the deforestation, that might lead to a more increasing variability. So that is a very potent mix for even more water stress. High urbanization rate, more people living into the city, and this deforestation is ongoing. So if we take that to a broader scale, by 2040, a lot of countries in the world will face a very high water stress. As cities actually swell in size, supplying water to an increasing population and water sources that are depleting, that creates water stress. And water stress has a deep impact on our daily life in both industry, and like I said on the first slide, industry, your daily home, and infrastructure or agriculture. So cities are now implementing new methods of water management. There's seawater desalination on the coastal regions, recycling grey waters for potable and non-potable use, rainwater management, splitting wastewater from rainwater, or a combination. If you look at a city like Singapore that does a combination, and in Namibia, Windhoek, actually 26% is of the water supply comes from reused water. And this has been going on for quite a while in some cities. Like in New York, there's been a building called the Solaire. It's one of the first buildings in America that had a LEED Gold certificate. And they implemented quite a lot of water-saving features, low-flow fixtures, rainwater collection, grey water reuse. So, and this water was actually being reused for toilet flushing, air conditioning, makeup water, and irrigation of a small park, so the landscaping around it. If you have a landscape, it's a livable city, but this water has to come from somewhere, and it takes up a lot of water. So the results of these buildings was a 50% reduction in potable water use versus a normal building in New York. 60% less sewage per apartment. The stormwater runoffs, they were able to use 170,000 gallons of water per year used for the irrigation. So that's actually quite a lot and a good saving. And this was already in 2003, so it is possible. If we have one slide on seawater desalinization on the coastal regions, it can be used for potable water or boiler water. It can be used for many things, but it's actually a very expensive and high energy consumption process. So it's typically a last resort measure that you would see on coastal regions like the Middle East, Australia, or dry regions anywhere else in the world. And a future trend will that wastewater will be managed more decentralized. In the past, your sewer would go to a municipality, and that would treat the wastewater, and then it would go into the ocean or something, or would be reused. But especially in tall buildings, decentralized systems will become more popular. It has some disadvantages. You have a high initial investment cost. And you have the operation and the maintenance of this system, but it actually has advantages that you have a lower cost of water supply. You can read faster than I can say it, but some of these things are greater resilience when there's water shortage, lower cost of the infrastructure that is actually around the building, because if we're having more people in the cities and we're using the existing infrastructure. If you reuse water in a tall building, it actually decreases the stress on the current infrastructure. And a closer look at grey water treatment technologies. It's a typical 2 or 3 step process to reuse the wastewater, depending on actually the use. If you're in close contact with the water, you need a a disinfection in the end, and if you are using it for toilet flushing or irrigation, actually you might not need the disinfection. But most of the time this treatment technology is preceded by a pre-treatment to remove solids out of the water. And if we have a closer look at the technologies that are behind actually this process, and I won't pretend to know all of them, actually this is supplied by the industrial side of Aliaxis. But if we have a closer look at the biological process, this is a membrane biological reactor, and that's actually a very good process and very much suited for high-rise. If you look at a membrane filter, it actually has a very high capacity to filter out the solids out of the water. And when that happens fast, that means that the residence time in these storage tanks can actually be shorter. And a shorter time means that the tanks can go smaller. And smaller in a tall building means less consumption of space that you could use for car parks or other services. So this space is a premium. Maybe a little bit technical, but if you see the requirements that different countries have, Germany, China, and the USA, on the minimum requirements that water has to conform to for toilet flushing. We're talking about certain factors: BOD, biological oxygen demand, the nitrogen, fecals from black wastewater. So if you take that in total and rank it, organics matters need to be removed. Bacterial load needs to be removed. Turbidity, or the transparency of a fluid, of a liquid, needs to be low. So if going to the third slide, membrane biological reactor basically ticks all these boxes. So this is being used more and more in high-rise buildings. And actually in countries like India, decentralized reuse of wastewater in a single building is already enforced. So if we come to the plumbing systems, and this is my background more, you look at all these pipes that go through the building. So there are pipes for grey water, there are pipes for black water, and most of the times these pipes are actually combined. Well, is this actually something that is beneficial for the process of reuse of wastewater? Well, if you actually combine them, that might be good for less pipe systems and a more affordable plumbing system in your building. It actually has a negative effect on the treatment system. So if you have grey water and black water in the same time, black water actually needs a higher resident time in these tanks, meaning larger tanks. And also, if you look at this process, it's much like a fish tank. You have fish, you have food, and you have oxygen. And this combination is a very set ratio, so that needs to be in tuned. And when you introduce black water, this process is very more difficult to manage. And also, when you start introducing grey water into black water always has some kind of human interference. And you have chlorine in your toilet or ammonia. And that actually upsets also this biological degradation. So that's also a very sensitive process. So combining these systems is actually not good. And if you have decentralized use of reuse of wastewater, you actually have to have split pipe systems. So that means more and more and more pipes. If we're looking at big high-rise buildings, you might have 13 to 20 stacks in a total building and duplicate that by 2 with the grey and black. So on rainwater, can rain and balcony water be combined? Well, again, if water comes from a roof, it's clean water. But actually, if it comes from a balcony and I'm cleaning my balcony, you can have detergents in it. So actually, the process of combining these two flows is also not beneficial for treating or combining these two flows. So it's the same as black and grey water. So some of these initiatives that are going on, and if you look at a city like, or a country like the Emirates in Dubai, where you might find very iconic buildings and prestige projects, well, actually it's shifting a little bit now that they're also wanting sustainable, high-quality buildings for the people. And the BREEAM in the Gulf actually has the whole sustainability factor weighted at 30%, so that's a very high rate. So coming back to Sydney, the Sydney water program that Monica touched upon this morning, if we look at the city of Sydney, 20 billion liters of stormwater runoff annually, 28 billion liters of wastewater is collected. So that's a staggering amount of 48 billion liters of water that is not used. So one of the expected results that the Sydney program wants to have is actually reduce to 50% of the water demand by 2030 with a whole set of enabling actions. And I won't list them all, you can read them in the proceedings. This is actually a detail out of the Sydney plan. So it's very interesting. So Sydney is working on this because, like Doug touched upon, Sydney will be growing by the next decades. So other trends driving these initiatives for decentralized reuse of water, of course it's LEED. We see a very large annual growth of LEED certified buildings, already 80,000 projects certified with LEED across the globe. We see legislation, we see local water programs like in Sydney that are driving these initiatives. And one important factor that we should not forget is actually the cost of water. I come from the Netherlands, water is almost for free, so why would you save it as a consumer? But actually, as these prices of water will rise and rise and rise, the consumers will also have a say-so in this matter. If you look at Melbourne, 6% annual increase of waste or of clean water will put a price stress on this water as well. So high-rise will adopt zero liquid discharge models, and this is a term out of the industry. But simply put, it basically means that all the water that you take out of a building, it has to be treated in some way. So it cannot go back into the ocean or it cannot go back into irrigation without prior treatment. So everything that you take out of the building must go into the building in some way. And it's a holistic view, and one of the last slides of Doug, you have to see the city as a whole. So if you have a closer look at the things that Aliaxis does, the building plumbing components of a zero liquid discharge systems are rainwater management, and I have now displayed it as a single pipe, but actually if there's a residential high-rise building with balconies, you have to have a split system. It would mean that you'd have a potable water supply from the municipality, but you also have another water supply for the non-potable. This from the decentralized reuse of rainwater at the treatment plant. And then on the drainage side, you need a split system, grey water discharge and black water discharge. So there's actually more piping system going into the building. And when there's more piping system going into the building, these service shafts need to be bigger, and architects and engineers need to cope with that. So in conclusion, just a little plug on Aliaxis. Of course, we strongly support these initiatives. We have several, or globally, we have a lot of solutions for rainwater management, a siphonic system. We have in Malaysia, where it rains a lot, rainwater drainage systems. Potable water supply, non-potable water supply, and that actually makes a difference because potable water supply can also be high temperature and you need different materials. So we've got PPR, CPVC, PEX, PVCU, all around the globe. Grey water, DWE, drain waste vent, and black water, DWV, in polyethylene, PVC, polypropylene, serving both acoustic, non-acoustic regular systems, and active ventilation technology that actually works when the buildings get higher and higher. You actually can do it with a single stack system. So you can read more about these systems on our website, on the Solution Finder. You can actually see where these systems are available. In a final, thank you for your attention. And